Oh. Okay. So I've been told if I do work, instead of doing board work, if I do it on the document camera, it'll be captured as part of the lecture. So then if you want to go back and see as I do it. So I'm going to try to, usually I like to use the board, but I'm going to try this way for a little while anyways. So let's see. It says, number 6 on page 41 says, the Informs Operations Research and Management has contracted with Sentinel Security to provide security for its upcoming 3-day, 4-night meeting in New York at a cost of $B. So what we should do, I guess, as we go is write down, kind of the data that we have. So we have, 3 days, and we have 4 nights. That is a parameter that's given. And the total income or the revenue or the fixed contract is $B. Okay, so $B is the contract price. Okay. It says during the meeting from 8 a.m. to 6 p.m. Sentinel will pay its security guards $D per hour. So the day is, let's write down the day appears to be, maybe I'll zoom out a little bit. The day appears to be 8 to 6, that's what, 10 hours? And the night then would be 14 hours. And it says the day rate is D. That's day rate. And the night rate is E. Evening rate. Okay. Let's see. It also says, okay, Informs requires that at least N guards be on duty during the evening. So at least N during the evening. Just trying to write down all the pertinent information. It says during the day should be at least 2 guards as well as 1 for every additional 1,000 attendees. So day is 2 plus 1 per 1,000. Okay, 2 plus 1 per 1,000. In addition to paying for its guards, Sentinel Security expects to have fixed expense of F. So F is our fixed expenses. And net profit to the firm is obtained by subtracting its payments to its guards plus the fixed expenses from the contract amount negotiated with Informs. It says formulate a model shell for this simplified problem, the objective of which is to maximize the net profit to Sentinel Security for supplying security service for T attendees. So I'm going to write down T is the number of attendees. And using the following decision variables, X1 is day guards and X2 is evening guards. So X1 equals day guards and X2 is evening guards. Now, what you'll find in this course, I hope, is as you do these, as you do more and more of these, it gets easier, right? Because for the first couple of weeks, we're going to be looking at constrained optimization models. And it's really trying to pick out the 3 things, like what can we decide, what are we trying to maximize, and what is holding us back, what is constraining us. That's what it's all about, those 3 things. And students typically struggle with going from the word problem to the model. They don't struggle as much with the Excel component because it's kind of the same thing over and over again. Okay, so I think as you start to read these and start to do more of them, you'll start to think that way. You'll be like, oh, that's something we can decide. That's something holding us back, okay? So let's try to identify those three things in this situation. And you guys help me with those three things. I don't know if I'm going to have room, but help me with those three things. So let's start out with what I can decide. What can I decide in this situation? It actually tells me what I'm deciding, right? What can I decide? What is Sentinel Security trying to figure out? What can they control? Cost. How do we control cost, though? You're right, we're trying to control cost, but by doing what?
Number of guards.
Yeah, the number of guards is what our decision variable is. So our decision variables is x1 and x2, where x1 is number of day guards, and x2 is number of evening guards. Okay, that's our decision variable. Now, the second thing we always have to think of is what are we trying to optimize? Remember, this is a constrained optimization model. What are we trying to optimize, make optimal? And make optimal means maximize or minimize. What are we trying to optimize in this case? And this is a common thing we try to optimize. Profit, okay. Now it tells us profit is calculated by taking the fixed contract amount minus our fixed expenses minus our payment to the guards, right? So instead of saying max profit, we have to make a max equation. We have to make an equation for that. So I'm going to definitely say max, right? I need to maximize something. The fixed expenses or the fixed contract price is B. I'm just going to put B, okay? That's the money coming in, whether that's 10,000, 50,000, whatever it might be. But expenses are eating into that. So one thing I know is fixed expenses. Fixed expenses, I think, was F, right? So minus F. Okay, and that could be, this could be 30,000, this could be 10,000, but they're keeping it as a variable at this point. Okay. Now we also have to subtract out our day guard. How much we pay our day guards. How do I get that? So I have 3 days. X1 is the number of day guards I hire, and I'm contracting them for the whole damn event. And a day is 10 hours, and we're paying them D dollars. So what does that look like? So 3 days, 10 hours a day, that means they're going to work how many hours? 30 at D dollars per hour. So 30 times D times X1. So minus 30 dx1, where if D rate is $10 and we hire 10 guards, then that looks like it's, what is that? That's $3,000 we're going to pay. Does that make sense? So if the rate was $8 and we hire 5, $1,200, right? So we're variabilizing that. Evening guards, we have what? 4 nights, 14 hours. That's what? 56 hours. So minus 56 E is the evening rate, X2. Okay. So that is our objective function. And it's sometimes harder in a model shell because it's easier to work with numbers. Those are less abstract than B dollars or F dollars, right? If you say I'm going to pay you B dollars, you're like, what does that mean? But if I say I'm going to give you 20,000, you know what that means. So this is, sometimes we create a model shell because we're going to use it over and over again. Like if I'm Sentinel Security, maybe every event I have is set up this way, right? So I just make them variables instead of plugging in 50,000 and 10,000 because that changes from event to event. Does that make sense? So if I built this as a spreadsheet, I'd make it very variabilized, I guess is the word. Okay. So we have 2 things done. We have our decision variables and we have our objective function. Now, as we went through there, you may have heard some constraints being mentioned. What kind of constraints did we hear there? You guys hear any constraints? Okay, so number of attendees that's something we can't control. That's something that happens. But how does that get factored in, Maria? You're right. Right, because up here you remember that says, hey, during the day we need 2 at a minimum plus 1 for every 1,000, right? Yes. So that's a constraint. That's something we have to have. So we're going to say x1 has to be greater than or equal to 2 plus, now this is where I have to kind of think mathematically. If I have 1,000 attendees, how many extra guards do I need? One extra. If I have 2,000 attendees, how many extra guards do I need? 2. So what mathematical operation is going from 2,000 to 2? How am I getting from 2,000 attendees to 2? I'm dividing that 2,000 by, so 2 plus t divided by 1,000. Does that make sense? So if it's t is 5,000, 5,000 divided by 1,000 is 5, and I need 7 guards. Does that make sense? Yes? Okay. Well, that should be x1 because we're talking about day guards. What does it tell us about evening guards? It says evening guards at least n during the evening, so it didn't even tell us what n is, but x2 is greater than or equal to n. That's just some variable, right? It doesn't even tell us what that is. So the other thing, okay, what else, and this is something we kind of didn't cover, but what else about x1 and x2? What else? I think that's all the, like the real constraints in there, but what else about x1 and x2? Sarah?
They have to be integers, it has to both have to be greater than 0.
Okay, first off, non-negativity constraint. We can't hire negative guards, right? There's people that do negative work, I know, but we can't hire negative guards, so we're going to say x1, x2 greater than or equal to 0. And in this case, we're just saying we either contract you for the event or not. So we can't really hire 0.25 of a guard, right? So the other constraint that we would build in is we just say all x are integer. Now, I'll talk a little bit later in this class why, in general, we want to avoid the integer constraint if we don't have to put it in there. Okay, it hurts something we do later. So a lot of times, like say we're making something, maybe we're making, let's say we're making 2 products and we're making, why am I struggling to think of a product? But let's say we're thinking of making 2 different types of cell phone covers. And you're saying, well, I can't make half a cell phone cover. No one builds half a cell phone, buys a half a cell phone cover. But we don't want to use the integer constraint because who cares if it comes out to make 3,800.5? We can always round up to the next one, right? And an integer constraint takes away some functionality for us later. So we're going to try to avoid that integer constraint. Does that make sense? Unless we have to. If we were building battleships, which are not nominal things, you know, they cost billions of dollars, then we'd want to make sure we include the integer constraint. And in this case, too, I would include the integer constraint, but not always. Not always when things are integers should I include that constraint. I think that's it. So let's look at whoops, a little further. And it says, formulate a model. I did that. Explain why the problem of maximizing net profit is equivalent to minimizing the variable cost of payments to its security guards. Someone want to take a shot at that? So if I look at this deal, it's saying why is this equivalent to minimize the variable expenses, if you will? Right, this is what it is. This is fixed expenses. It's 8,000 or whatever it is. This is the contract coming in. So if we want to maximize this whole thing, we really want to minimize this component, right? So if I rewrote this whole thing like this, minimize 30 dx1 plus 56 ex2, it would give me the same exact answer. No matter which way I did it, it would give me the same exact, because these are eventually going to be constants, right? So it would give me, I swear to you, if I solve this, it would give me the same exact answer. Let's look at number C. Informs, expects 2,000 attendees, and it wishes to have at least 2 guards on duty each evening. So it's starting to write in these variables. It says they're going to have 2,000 attendees, so T is 2,000. It says it wants N, it wants 2 guards. This is becoming a 2. It says the contracted price is 10,000, so this is 10K. It says fixed expenses is 1,000K. Okay, it says we pay our day guards $15, so D is 15, and we pay our evening, what did it say, 12? 12. So all we're really doing is, we're taking this, what was a model shell, and we're plugging in what we know. Okay, so I would just do that. I would say, all right, this is 10,000, this is 1,000, minus 30, so D, the day rate is 15, so times 30, that would be what, 450. X1, every day guard is going to cost us $450, and every evening guard is 12 times 56. What is that?
672.
672 plus 672 X2. Okay, this becomes, I think they told us 2. They said how many attendees? 2,000. So that becomes 4. All we're doing really is putting in, taking those variables and plugging in the actual rates for this job. Suppose his attendance is expected to be 2,200. Now what would be the model? Well, if attendance is 2,200, 2,200 divided by 1,000 is 2.2. 2.2 plus 2 is 4.2. Would we ever, because of the way the constraints are written, will we ever hire 4.2 guards? No. What's the minimum number of day guards we would hire then? Not 4, 5, because it has to be greater than or equal to 4.2, and these are all and constraints. They all have to hold, and it has to be an integer. The first integer greater than 4.2 is 5, right? So it would be 5 would be the minimum number of guards we could hire in this case. This is sometimes a little bit abstract, like the model shell is. But model shells are, if you work for a place and you do a lot of these gigs, you are Sentinel security, and you want to figure out, how many guards should I hire, and what does that look like? Well, you would build this in a spreadsheet, and you would say, all right, put in the fixed contract rate, put in the rate we have to pay in this area, how many attendees do we expect, and you'd set it up in Solver, and then every time you'd solve it and give you the optimal solution for that gig, right? For that contract. So model shells are just taking a linear program and making it more variabilized so that we can reuse it over and over and over again. So once it's built well, an organization can use it over and over and over again. So that is number 6. Does that make sense? Yes? No? Okay, one other I'd like to do, and I'm not going to, just kind of thinking about it, is number 7. And what's good about number 7 is I think sometimes we get stuck in the rut that, hey, this is, we're slaves to the math, and that's not the case. And this is a tool that can be used to help you make managerial decisions. And there are situations where different people may look at it differently, like the things that we want to optimize. Okay, and this is an example of that. This is a bad example, but it's an example of that because it has some crazy assumptions built into it, but it's an example. Plus it's using, you guys can really see the age of the text here, like compact. You guys remember compact computers? I think HP ended up buying them, I think, and that's probably 10 years ago, wasn't it? Circuit guys, I think that's a veiled reference to also dead, right? So yeah, I mean, IBM's still around, but they sold all their laptops anyways to Lenovo. They sold the branding rights. So you can see the age of this text. Anyways, sometimes different managers, executives approach the same data with different objectives. Circuit Guys is a retail computer store that displays the latest computers from Compaq and IBM. The store averages a profit of $200 on every Compaq and $300 on every IBM. For each Compaq system displayed, the estimated probability that Circuit Guys will sell, the estimate is 0.02. sell a system is 0.02. Each IBM system displayed has an estimated probability of 1% of selling that day, which is a crazy assumption that the odds of us selling are equivalent to how many we display. That's a pretty poor marketing assumption, but for the purposes of walking instead of running, let's do it this way. So it says, one manager at Circuit Guys suggests that since it's a new store, it should maximize the total number of units on display. Write the expression that models this objective. So our decision variables would be what? What are we trying to decide? What are we trying to decide? Haley?
X1 and X2.
And what is X1 and X2, Haley?
It's like 200 and 300.
That is the profit we make for each sale of a Compaq and IBM.
Is it controlled?
That is the probability of them selling once we display them. But the thing that we can decide as the store manager is what? What are we trying to decide here? Yes, sir.
How many people you display?
Yeah, how many we're going to put out to display, right? So let's make it easy. Instead of X1 and X2, which I'm going to use C for number of compacts. I briefly forgot how to make a P. Compacts to display. I don't write anymore. I type, right? It's hard when you write. And I is equal to number of IBMs to display. Okay. And it's real important that you define your variables as what they are, right? That's what we're deciding, the number to display. So the first one is they want to maximize the number of units on display. So don't overthink this. What is the objective function then? Maximize the number of units on display. Don't overthink this. It would be what?
C plus I.
That's it. Maximize C plus I. Now, this isn't a full model, but obviously, right now, we would display an infinite amount of Compaqs and an infinite amount of IBMs. But what are likely other constraints that this store manager has to deal with? Yeah, he only has so much display space, or she only has so much display space, and inventory, right? Those would be constraints. We only have this much square footage to display stuff. We only have that much. So that's missing from this equation, but it's just trying to look at the objective function at this point. Another manager feels that the way to impress corporate headquarters is to show a large number of sales at the new store. Write the expression that models that. So maximize. And we have to go from our decision variables to sales. And what we're saying is, there's a 2% chance when we display at Circuit Compaq it'll sell, and only a 1% an IBM will sell. So that would be if we display 100 Compaqs, 2 of them would sell. And if we display 100 IBMs, 1 of them would sell. So we'd maximize 0.02C plus 0.01I. Does that make sense? We're trying to go from that decision variable to sales. And that's the translation, which is a crazy translation, I get. But that's the context of this problem. And the third one says, so another manager believes that the bottom line is what is important. He feels that in the long run, maximizing expected profit is what the stockholders want. Write the expression that models this objective. So looks like we make $200 on every Compaq and $300 on every IBM. So it'd be maximize 0.02 times 200 C, because we sell it, this is how much we make, plus 0.01 300I, so this becomes 40C plus 30I. Now, I know that's a crazy assumption that you display it and it sells. The more you display, the more you sell. But my brother he's the current manager of the Lowe's in State College, and I think he's moving next week to the Lowe's in Johnstown. And he tells me that if they take like say air conditioners, they leave the same price on them, but they stack them like toward the entrance, in like a pyramid. He said sales go up like 50%. Which is crazy, right? The same price, because people think, hey, they must be special. They're stacking them in front. They're making a pyramid of them. So there's a lot of stuff that can be done to sell things. But anyway, that's neither here nor there. So any other questions on the homework? You guys were able to do this without much issue? Okay. Good, then we'll move on. All right, so some of this, little bit of review, and we're going to do a couple things tonight. So we're going to stay in chapter 2. We're kind of done with chapter 1. So we're moving into chapter 2, and we're going to spend 2 weeks in chapter 2. Okay, so today, a couple things that we want to understand better. We want to still continue to practice to move from a book problem to a mathematical model. We're going to also practice solving them in Excel. And I'm also going to show you like an old school method to solve them. Okay, it's called the graphical method. Now, I'm going to show you that method to solve them, but we're never going to do it that way. And you're saying, well, why are you showing us that? Well, because what we're learning next week, okay, is a concept called sensitivity analysis. And it sounds like some kind of HR training that you guys were forced to go to. But it's not. It has to do with understanding, hey, I have a solution, I have a solution to my model. How sensitive is it to changes in particular variables? And it's really a powerful tool. It's a difficult concept, but I think when we show it graphically, it kind of helps with things a little bit, okay? So a linear model, which we're talking about, consists of 3 things, as you guys know. A set of decision variables, an objective function, and a set of constraints. And what's nice about this linear programming is there's a lot of real-world problems that can be approximated by linear models. So that's an important word, approximated, because it's not exact, right? It's never exact, but it can be approximated and it can inform us and give us some knowledge where we had no knowledge. And there's a lot of well-known successful applications, manufacturing, the product mix model, which is the corn and barley problem we did was kind of a product mix problem. It was how much of corn to make and how much of barley to make. And sometimes, manufacturing firms say, I have a line of products, maybe 10, 15, 20 products. I only have so much manpower, so much material for this next production run. How much of each should I make? Okay, so production mix is a big application, manufacturing. Marketing. Some of you were undergraduate marketing majors or in marketing discipline. If you think about it, a lot of times we only have so many dollars to spend, right? And we have different venues we can spend those dollars. It can be on the web, it can be radio, it can be TV. And maybe you're looking at impressions, you're looking at a return on investment as things you might want to maximize. So you're trying to decide how to best allocate your advertising budget, but there might be constraints. Maybe you already have a contract. So those are good applications of this. Finance, if you think about finance, you're deciding how to invest your money. They're called portfolio models, right? I want to invest my money among these portfolios, among these different investments, but I maybe want to minimize risk, but still lock in a certain return, a rate of return. So we'll talk about those kind of models. Agriculture, we saw those kind of things. The nice thing about linear programming is if we can take a business situation and we can approximate it as a linear program, well, we can solve it pretty easily with solve, okay, which is nice. So we have a solution technique, and further, what's even better is we can get our solution and then we can do what-if analysis after. We can say, well, what if the cost changes, or what if we were wrong in our assumption when we said we were going to make this many dollars for every acre of corn we planted? We can do those kinds of things pretty efficiently. So give us a lot of information, not just the solution, but a lot of information to go around that solution. Okay. So I've been talking about the greatness of linear programming, and I'm going to take a step back because linear programming also has some assumptions that we have to buy into that are often violated in real world. Okay, some things that for us to use linear programming, we kind of have to buy into the assumptions that we say, well, you know what, we really violate this when we look at it in actuality. So the first one is the parameter values are known with certainty. So when I'm deciding, let's go to the corn and barley problem. When I'm planting corn, do I know how much I'm going to make per acre on corn? No. Do I know how much I'm going to make per acre on barley? No. It's an estimate, right? But for me to use this, I have to make the assumption that I know it with certainty. So that's kind of a drawback, right? Because I don't know, maybe there's going to be a corn shortage, I'm going to make more if my corn comes in, or maybe there's going to be a corn surplus, I want to make less. So I don't know that. Okay, so that's a drawback that we have to make that assumption. It says the objective functioning constraints exhibit constant returns to scale. So, and we know we violate this in the manufacturing world all the time. For example, if I make a prototype for something, like I make one of something, it might cost me a couple $1,000s. But if I make 100,000 of them, hell, it might be 50 cents each, right? So we have to say constant returns to scale, like the next unit costs as much as the 1,000th unit costs as much as the first unit. Does that make sense? Because it's linear. We're talking about linear programs, so it has to move according to a line. But we know, in practice, sometimes that's not true. That's an assumption we have to make. The third thing is there are no interactions between the decision variables. It's called the additivity assumption, and we violate this sometimes. For example, we have to assume that maybe product B and product C are related. Like one is, I don't know, like the residential version of this product, and one is the commercial version of this product. So making them together is more efficient. But we have to assume there's no interaction between that. We have to treat them separate, right? And we know sometimes there are some interactivity things that go on in real life, but we have to assume they do not happen, the additivity assumption. And the last one is the continuity assumption. So variables can take on any value within a given feasible range. And we know, we've already shown that sometimes we're talking about integers, so that's not continuity. It goes from 5 to 6, 6 to 7. It's not a continuous line. So we violate that. So I just told you how great linear programming is and how wonderful it is in the world of business to solve so many things in agriculture and advertising and finance and marketing. And then I said, well, we have to make all these assumptions that we routinely violate in real world. So what good is it? Well, you'll see, that's what we're going to kind of talk about next week, is we're going to have an answer, and we're going to say, but we baked all these assumptions in that we know we violated, so how good is this answer? Well, we're going to do sensitivity analysis and say, not only is this the answer, this is the answer if, for example, corn yields $20 per acre or $1,000 per acre. This is still the right mix of corn and barley to make. So we're going to have a solution that's going to tell us where that solution is valid in. Okay, so that's kind of next week's stuff. But I wanted to say, look, that's why these assumptions are important, but that's why we can routinely violate them and still get usefulness out of this thing called linear programming. Okay. So what we're going to do, okay, is we're going to do one, and we're going to do one from scratch again. Okay, we're going to do it with we're going to do it graphically first. Okay, so that's how we're going to start with this. And we're going to do something called a production mix model. And a production mix model is kind of a standard application of linear programming that is used a great deal in the business world. Okay? And sometimes this is baked in the software, so you don't have to come up with it yourself. but sometimes you do. So this is on page 50. And I'm not going to read it all to you because that is extremely boring. But I want to give you the gist of it, and then we're going to kind of look at some of the parameters, okay? So then, and as I read it, I want you to write down some of the things, you know, that you would say, these are the things we can decide. This is the thing we're trying to maximize or minimize. And these are our constraints, okay? So we are Galaxy Industries, and we make two types. I'll probably make a lot of things, but for this thing, we're saying we make two types of, I think these are squirt guns or water guns. And those two water guns are called the Space Ray and the Zapper. Well, we must not have very creative marketing people. But the two of the limiting resources, this is on page top of 51, are 1,000 pounds of a special plastic compound and the 40 hours of production time that are available each week. So what does that sound like to you when I said limiting resources? What automatically should you say that's going to end up where? That's a constraint, right? It's going to go down in the bottom. We also have, so that's a physical constraint, kind of a hard constraint, like it's, you know, physical, so it's a hard constraint. But we also have discretionary constraints because our marketing department says, hey, we want to build a strong customer demand for the fledgling company's things. So our marketing department has put in two other constraints on us. They said, we're not going to make more than 700 dozen units. That's the most we can make in a production run. Don't make any more. We don't want to flood the market. And it says, you know, and to prevent weekly production of Space Rays from exceeding that of Zappers by more than 350 dozen. So we can make more Space Rays than Zappers, but not by more than 350, right? So if we make 100 Zappers, the most Space Rays we can make is 450. Does that make sense? Like the difference there can't be more than 450. Does that make sense? And we know as we produce these things, we are hoping that when we sell a dozen Space Rays, we net $8. And when we sell a dozen Zappers, we make $5. And we know they consume resources. Plastic, so this one takes 2 pounds of plastic per dozen. The Zapper takes 1 pound. We know the production time is, it takes 3 minutes per dozen of Space Rays and 4 minutes per dozen of Zappers. So first thing is I want to go from this to the constrained optimization model. So I'm going to go to my document camera. And I want you guys to help me get there. And then we're going to solve this two ways. We're going to set it up, but we're going to solve it two ways. The first way is the old school way, okay? And I'm going to show you that. You'll never have to do it. But there's some terms in there, some terminology, some techniques that you need to know. So first thing, what are our decision variables here? What are our decision variables? Okay, and I want you to be more specific. I struggle with that word for some reason. Okay, good. What's she missing? You're good. I'm just yes, exactly. Okay. So if you thought about it, everything was in units of dozens, right? It said number of the 4 minutes per dozen. It said $8 per dozen. So our X1 and X2 are going to also be in dozens. X1 is the number of dozens of Space Rays. And X2 is the number of dozens of Zappers. And it's really important that we think about units on our variables, right? Because we're not just making Space Rays and Zappers, we're making dozens. And if I think about that, now I'd be much less likely to use the integer constraint. Why? Because I can do what?
Dozen.
I can make a half dozen, right? That's 6. I can make 6. But even if that weren't the case, I wouldn't use the integer constraint because these things are pretty nominal things, right? These are, so what if it said make I don't know, 83.6 space rays. Well, I'll just make 84. Who cares, right? And we can always say, well, that 0.6 is work in progress or something like that. So I would never use the integer constraint on this anyways, but that's another reason not to. All right, so what is our objective function? What is our objective function here? What are we trying to maximize or minimize? What are we trying to maximize or minimize here? Profit, very good. So I'm going to maximize, and I could write profit, but you know that's not going to be understood by Excel or the math. So profit as a function would look like what? The objective function would look like what? Let's go back to our little table. So we make $8 per dozen profit for space rays and $5 per dozen zappers. So what would that look like here? Maximize what? If we make one dozen of each, we make 13 bucks. So 8x1 plus 5x2. Does that make sense? If we make 2 of each, hey, that's 26 bucks. We make 10 of each, that's 130 bucks. So usually those are the two easier things to think about. The constraints, a little more difficult. As we went through there, so subject to, as we went through there, what did you hear constraint-wise, things that were holding us back? Physical constraints. Let's start with physical constraints.
Plastic available?
Yeah, we only have, it looks like it told us we have 1,000 pounds of plastic. So that's going to go on the right-hand side of our equation. That's called a right-hand side constraint. So 1,000, and if we make a dozen zappers or space rays, according to that table on page 51, that consumes 2 pounds. And if we make a dozen zappers, that consumes 1 pound. So if we make 1 dozen of each, that's 3 pounds, right? So that left-hand side, the consumption has to be less than or equal to 1,000. What else do you see holding us back? Yes, sir.
The space rays have to be less than or equal to zappers plus 350.
Okay, let's hold off on that one. That's a discretionary marketing constraint. Let's go to the other physical constraint, right? What's the other physical constraint? Yeah, we have people, right? People and material, right? So people is something. So if we look at the table, it says, all right, production time, every dozen space rays takes 3 minutes. Every dozen zappers takes 4 minutes. So let's do this. And this is going to be wrong, but let's say this is production time. I'm going to say 3x1 plus 4x2. That is wrong. Why is that wrong?
Minutes and hours.
Yeah, on the left-hand side I have minutes. On the right-hand side I have hours. So I could either divide these two coefficients by 60, which gives me decimals which are ugly, or my other option would be to do what? To make it the same units, to do what? Multiply the right-hand side by 60, and that gives me 2,400. So now it's all in minutes. Right-hand side has to match the left-hand side. Now, every equation wouldn't have to be the same, but if every equation, the left-hand side units have to match the right-hand side. But I could, if I had another deal down here, I could do hours and hours, you know, but as long as it was hours and hours on the both sides, okay? So those are like the physical constraints. So you mentioned we have some discretionary constraints, and a lot of times that's the case, right? Like you have physical constraints, but then there's also, you know, marketing wants us to do this. My boss, for political reasons, says we have to do this project. You know, whatever it might be. Those are constraints that we have to live by. So the one, and it says we can't produce more than 700 dozens. That one's pretty easy, right? We can pretty easily say x1 plus x2 is less than or equal to 700. Right? That's total the total production has to be less than or equal to 700. Now it says the difference, we can make more space rays, which is the X1s than zappers, but the difference can't be more than 350. So that was a tougher one to think about. So I can make, if I make 450 here, I can only make 100 here. I can't make 99 and 450 or 451 and 100. So that difference between the two has to be less than or equal to 350. So if someone help me write that, what would I write? And I got to have the difference on the left-hand side. X1 minus X2 has to be what?
Less than or equal to
350. Okay, so this doesn't prevent me from making, let me say we make no space rays and 100 zappers. Well, that doesn't violate that constraint because we're making 100 zappers more than space rays, and that's not what we said. We just wanted to limit the difference between the space rays and that. We don't want space rays to dominate, right? Yes, sir.
Wouldn't you multiply it by 12 because isn't X1 and X2 in dozens?
It is, but this is also, the constraint was also written in dozens.
Oh,
It said-
that is 350 dozens?
It is, yes, it is. Let's see where it says the number of dozen space rays produced weekly is X1. Let's see the actual text to confirm that. Yes. So on page 51 it says space rays from exceeding that of zappers by more than 350 dozen. So yes, it's all in dozens. All right. As well, what else would I need? We said we're not using the inner constraint, but what constraint would we still need?
greater than 0.
Non-negativity. So I would say x1 comma x2 greater than or equal to 0. Okay, so that is going from this problem, okay, to a full mathematical model. That's all we've done. We've said take this business situation, mathematically model. And as we did this, you may have noted that there's probably constraints in there that, assumptions that we had to make that we violated, right? Constant returns to scale. I'm sure that that 800th space ray doesn't cost as much as or the 500 space ray doesn't cost as much as that first one, but we have to assume that they all use the same amount of time, whatever it might be. So as we look at this, and this is what we did together, it tells us right now management is doing this. This is how they're doing it. This is like their rule of thumb. They're making $4,100 per week and wants to know if we can do better. So we said, yeah, you know what? We're going to set this up as a constrained optimization model, and this looks like what we did, right? These are the values that we did. We did the non-negativity. But now we want to solve it. Okay, now we want to solve it. So this is probably a good breaking point. I'd like to do like an hour first and then take like a 10-minute break. So let's break right now. And I'm going to come back. We're going to show you how we solve this thing graphically. And as we solve it graphically, there's going to be some terms we need to define, some concepts we need to understand. Then we're going to solve it with Excel. And we're probably going to do a couple others with Excel, because that's, once we get there, I think that a lot of people struggle with the Excel part. So I'll show you some tricks there. So take like, what is it? It's 24 after, I don't know, come back at 25 till, I guess. That's like 12 minutes or 11 minutes. Okay, so before we had marvelous things like spreadsheets, mathematical modeling was much more difficult. In fact, even when I first started teaching this course, I would make people do at least a couple with the graphical method, but we don't have to do that anymore. But it still does make sense to go through it to kind of see what's happening and kind of envision how we're coming up with a solution, okay? So we're going to take that same problem that we just did, where we're making space rays and zappers, and we have a production mix, maximize 8x1 plus 5x2, and we're going to solve it. So we can model it, but that's not the solution. We want to come up with a solution, like what's the best production to make. So the way we start with that is we first look at the constraints. We look at those constraints on the bottom, those subject to those lines, and those define what is feasible and what is not feasible, right? It says, hey, we only have so much plastic, and we only have so many hours, and we only have, marketing is holding us to 700 units. So all those constraints are and constraints, meaning this has to hold true, and this has to hold true, and this has to hold true. So those constraints build what we call a feasible region, a region of all the points that are possible, and it also gives us all the points that are impossible. So what does that look like? Okay, so first off, let's take those constraint at a time. The first one is the non-negativity constraint. So if we think about 4 quadrants, we're saying if x1 is the number of space rays to make, and the y-axis we're calling x2 is the number of zappers to make. So go 2-dimensional. Everything on the x-axis is number of space rays. Everything on the y-axis, number of zappers. And the first thing we said is we have to make positive of each. Well, that limits us now to quadrant 1. This quadrant's out, this quadrant's out, this quadrant's out. So, we've eliminated an infinite amount of points, but we still have an infinite amount of points. So we're still working on this. The next one, the plastic constraint. Okay, you think about it. This is space rays, and this is zappers. And the plastic constraint said 2x plus 1 plus x2 is less than or equal to 1,000. So if you think about it, to graph a line, we need what? We can do it with 1 point and a slope, or what else? How else can we graph a line? 1 point and a slope, or
2 points.
2 points, okay. So let's get 2 points. If we make no space rays, x1 is 0, what's the most zappers we can make? Well, 1,000, 0, 1,000. If we make no zappers, well, we can make 500 space rays, right? So that's that line. We just graphed that line. What we're saying, it has to be less than or equal to that line, right? Less than or equal to that line, and in the quadrant. So we've just done what? We've eliminated all of these points in purple because they use too much plastic, yes? These are ones that don't use too much plastic. So we've just created a feasible region, but that's not the only constraint we have to hold to. We also have our production time. And if I graph that, 3x1 plus 4x2 is less than 2,400, it comes up with this, and it also has to be less than or equal to that. So these points, we have enough production time, but we don't have enough plastic, right? These points, we have enough plastic, but we don't have enough production time. So we're kind of down to that space, right? Now that we graph in, layer that in. So our feasible region is getting smaller. And if you think about it, more constraining means what? You don't want constraints in your life, right? You want unbounded things. Constraints make things less, more options unavailable to us. This is the total production constraint. And we say, okay, it has to be less than that line. Did that change our feasible region at all? No, okay, so we call that a redundant constraint because it doesn't hurt us. It still makes sense to put it in because some of these factors might change and it might become non-redundant. So we put it in there, but it didn't change it. And then we also layer in our discretionary constraint. Now, this, we have all the constraints layered in. This area is called the feasible region. So all the constraints, if we graph them, label them in, graph them, it defines the points that are feasible. How many points are up there in green? It's kind of a trick question. How many points are there? Nate?
A lot.
Okay, what's the most a lot you know? Infinite, right? There's an infinite amount of points here, are there not? There's an infinite amount of points on that line. There's an infinite amount of points there. There's an infinite amount of points there, right? A lot of points, okay? So what we need to do, okay, so we went from an infinite amount of points to an infinite amount of points. Hey, we still want to come up with one solution, one best way. Well, a couple things we know is when we look at a feasible region, there are three types of feasible points. And the first one is interior points. Those are points on the inside. All this green, all this green is interior points. If there is an optimal solution, an interior point is never an optimal solution. It's never an optimal solution. So all those points inside will never be an optimal solution. All right, so we just eliminated an infinite amount of points, but guess what? We still have an infinite amount of points because now we're talking about the border. The second type of points are boundary points, which makes sense. Those are points on the boundary. And boundary points may be an optimal solution. That's kind of funky, but may be an optimal solution. And just hold on. If there is an optimal solution, a boundary point may be an optimal solution. But hey, guess what? If we look at the boundary, there's an infinite amount of points on the boundary, so it doesn't help us. The third type of point are called extreme points. Extreme points are corners, if you will. This feasible region has how many extreme points? Well, 1, 2, 3, 4, and 5. It has 5 corners. And this is where we go from infinite amount of solutions to 5. If there is an optimal solution, an extreme point is always an optimal solution. So we went from an infinite amount of points to, hey, there's only 5 that could be the best. Okay? Does that make sense? So interior points are never ones, boundaries may be, and extreme points, if there is one, always are. But I don't know which of those 5. I'm guessing it's not 0, 0, right? Make nothing, that's the best profit. I don't think that makes sense. But I'm not sure if it's this one, this one, this one, or this one. So how do we determine that? Well, what is the thing we're trying to optimize in this deal? So those are the points that are feasible. What are we trying to optimize in this for Galaxy Industries? Profit. The profit line is 8x1 plus 5x2. So if we were to pick a value and graph that, that's the manufacturer thing. Let's say start at some arbitrary point like $2,000. This is that line. This is 8x1 plus 5x2 is equal to 2,000. But we can do better, right? And if we take that line and we say, all right, let's move it out. Move it out. This is the profit line. Now we're making $4,000 profit, $5,000 profit. And the last point it touches is the best point. Doesn't it make sense? Because this is the profit line, and I want to optimize profit. So boom, 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 push it out. The last point it touches is the optimal profit, right? The optimal profit is, looks like in this case, 4,360. Go ahead, Andy.
What makes it unfeasible or infeasible?
This one is feasible, okay?
No, and then the second part about continuing until it becomes infeasible.
Okay, so I want to take this profit line, which has the slope 8x1 plus 5x2, and I want to push it out as far as I can until it no longer touches, hey, these are all the feasible points. The last point it touches and still is okay, feasible, is that point, right? That's why an extreme point is always an optimal solution. Never one of these. When would this be like the optimal solution? This is an extreme point. When would that be the optimal solution? What if the profit line had a different slope? Like, what if it was 20x1 plus 5x2? That's the thing we're trying to maximize. Well, maybe the slope of that line looked like this now. And we push it out, push it out, push it out, push it out, push it out. Okay, now that's the last point it touches. Does that make sense? And if that thing had even a more extreme slope this way, maybe we push it out, push it out, push it out, push it out. And that's the last point it touches. So that's why an extreme point is always an optimal solution. Okay? Always an optimal solution. So this happens to be where two constraints come together. So that's always an optimal solution. You say, well, you know, how would I do that? Well, I could solve simultaneously for these two equations, which I used to make the class do and I don't anymore. And that would give us that point. You know, whatever that is, I think it turns out to be make 320 dozen space rays and 360 dozen zappers, and that gives us a profit of 4,360. That's that point. Go over 320, up 360. That's our optimal production, right? That's it. That's it right there. Now, that just produced, you know, it adheres to all the constraints. You know, we use all the things. Space rays production exceeds zappers, but only by 40 dozen. So well, it doesn't actually. Zappers is over space rays, and it increased the profit. I don't know if you remember what our rule of thumb. We were only making $4,100 for a production run. Now we're making 4,360. Now, why do I show you this? Well, think about this. So we went into this. We said 8x1 plus 5x2. That was our profit line. We said that 8 and that 5 were only like a guess, right? So what if it was 9x1 plus 5x2? Like what if we were making $9 a dozen for space rays? What would happen to this profit line? If we change that coefficient, it would slightly change the slope, but not a whole lot. And guess what? It would still be the last point it touches, the same damn point, right? So what that is saying, and we'll talk about that next week, is not only is that the solution, but it's going to be a solution in a wide range or somewhat wide range of variables. Okay, so even though we violate all of those assumptions, that's going to be the deal. Okay, so that is what is happening behind the scenes. The constraints define this feasible region. The profit line is we're trying to maximize it, so we try to push it out as far as we can. And the last point it touches is our optimal point. That's what our decision would be, our final decision would be. Okay? Now, we don't have to do this anymore. Okay? We don't have to do this anymore. We can use our good friend Excel. So let's solve it. But we're going to do the same thing, but we're going to use Excel. All right, so let's redo this problem from scratch. Okay, let's pretend like we didn't do the corn and barley problem last week, and let's redo this one. Okay, let's do space ray and zapper, and then I'll show you how we can reuse it. We'll do some more of these today. Okay, so let's go over here. Let's go over to C1 and D1. And let's put our labels. So I'm going to put space rays and zappers. I'm going to give them nice self styles. Center them just to be nice. And in C2 and D2, I'm going to assume at the beginning of this we're making 1 dozen of each. Okay, so C2 and D2 these are going to be my decision variables, if you will. This is where they're going to live. Okay. For clarity purposes, I'm going to skip a row, and I'm going to put max, and this is just a label. It doesn't do anything, it's just a label. I don't need it. And I want to think about the coefficients. What was the coefficient in the profit for space rays? The number in front of X1. 8. Very good. And for zappers, it was 5. Those are our coefficients. Okay, now we're going to build a little function here so that when we change the number of space rays and number of zappers, it changes profit appropriately. And let's just, I'm going to make profit a, I don't know, green because I want it to be positive. So I'm going to put in equal sum product is the formula. We talked about sum product last week, yes? So I'm going to give it two arrays. And the first array I'm going to give it is my decision variables, which is C2 comma to D2, colon D2. And the second array I'm going to give it is C4 through D4. Now I'm going to reuse that formula. And when I reuse it, there's part of that formula I want to be absolute and part of it that I want to be relative. What part do I want to be absolute? Nope, the point I want to reference always is the decision variable, so it would be the C2, D2. So I'm going to highlight the C2, D2 part and use the F4 function key. And it's going to put dollar signs there for me. It's not going to, and I hit enter, it's not going to change anything, but now it looks like, now I've fixed it, okay? So just make sure that when I change this, it's changing your profit accordingly. Make sure everything is referencing correctly. Yes, yes, okay. Let's skip a line and let's go over to A, and I'm going to put ST. And just for labeling purposes, I'm going to put plastic here first. And if you remember plastic, the coefficient for space rays was a 2. The coefficient for zappers was a 1. And I'm going to copy that down so it figures out the amount of plastic I'm using. And it has to be less than or equal to, and I'm going to come over here and say 1,000. Okay, and if I change, make sure when you change your decision variables, it changes both the amount of plastic you use and the amount of profit you make, and it does. Time, I'm going to write time here, and the coefficients for time were 3, 4. Copy that down. And it has to be less than or equal to 2,400, I believe it is. And once again, as I change everything appropriately. I'm going to make another constraint called total production. You remember x1 plus x2 has to be less than or equal to 700. Well, what's the implied coefficient in front of x1 and x2? 1, 1. Copy that down. Has to be less than or equal to 700. And I'm just taking what I have on paper here. That's what I have on paper, and recreating it with Excel. The last one is x1 minus x2 is less than or equal to 350. So that is, marketing x1 minus x2. So what's the coefficient in front of x2? Minus x2, it would be -1. Excel has finally recognized what I'm doing here. You see, and it said, hey, every time you're copying down, so I'll do it for you. Thank you. Less than or equal to 350. If it didn't do it for you, you have to copy it down. Or I could have waited to the end and just drug the thing down. But so make sure that when you change your decision variables, everything is predicated off that. So when you change C2 and D2, make sure that everything else changes appropriately, okay? You guys with me? So all we've done is take that piece of paper, fill it in a spreadsheet. All right, so now I haven't solved it, I've just translated it. Now I want to solve it. I'm going to go to Data, Solver. Solver needs to know where those three things live. First off, it needs my objective cell. What one cell represents the thing I'm trying to maximize or minimize? What one cell represents the thing I'm trying to maximize or minimize? E4 in my case. Might be different in your case, but profit. So I'm going to hit that little spreadsheet, click on E4, hit the drop down. I'm maximizing E4. Okay, maximizing E4. I told you about the objective function. By changing variable cells, what it's saying here is, what are my decision variables? What are the things I'm allowed to change? Very good. C2 and D2. That's what it's allowed to change. Now what's kind of nice, okay, and this works out good, because all my constraints, there's 4 of them, and they're all less than or equal to, okay? I can put them in as one. Like I can put them in as an array, a range. I can say everything in E6 through E9 has to be less than or equal to everything in G6 through G9 respectively. So I don't have to put them in individually. You guys know what I'm saying? Now if there was a greater than or equal to in the middle of that, then I have to deal with that, right? So sometimes people put all their less than or equal to's in a range and all their greater than or equal to, or you can put them in individually. It doesn't matter. I like to save as many keystrokes as I can. So I'm going to say add, and I'm going to click the little spreadsheet, and I'm going to say E6 through E9. That's in the left-hand side. Has to be less than or equal to G6 through G9 respectively. So it's matching them up. E6 has to be less than G6, E7 has to have G7, so forth and so on. I click add, it goes away, and you're like, what the heck happened? It doesn't give me a message, but let's hit cancel, which is scary to always do, but it takes us back to the dialogue that we're looking. So let's just give her a check. So maximizing E4 by changing C2, D2, E6 through E9 has to be less than or equal to G6 through G9. We didn't say X1 and X2 has to be greater than or equal to 0, but by checking this box, you see this box here? That does that for us, okay? That's the X1, X2 greater than or equal to 0. And then the solving method we want is simplex LP. So just change it to simplex LP always. We'll always do that. And the moment of truth is here. So I'm going to click on solve. And hopefully it says, hey, solver found a solution. All constraints and optimality conditions satisfied. You want to keep the solver solution? I'm going to click OK. And it says the one best way is to make 320 dozen space rays, 360 dozen zappers. That nets a profit of 4,360. Now, did you guys get that? Okay. If I look at this solution, I notice that some things are what we call binding. What is holding us back from making more space rays and zappers? And it's kind of easy to tell. What's holding us back from making more space rays and zappers? What am I using all of, if you will? Plastic and time. Do you remember where that optimal point was in the feasible region? Where what 2 constraints came together? Plastic and time, right? So that's what's happening there, right? That's the last point that it touches. And further, like next week, what we're going to concentrate on is, okay, we have a solution, but as a manager, we want to know what if, and we want to know how good of a solution this is. Next week, we're going to focus on that, like taking this solution to the next level. But right now, we have a solution, and we're happy. Okay? I could do what if analysis if I wanted. Let's say, I don't know, let's say I make, maybe space rays become, let's say zappers become wicked profitable. So, I don't know, they become 25 bucks. So now I click solver, I click solve, resolve, and now of course, being optimizing profit, it says, well, the hell with space rays, make nothing but zappers, and that point is 0, make 0 space rays, 600 zappers. It's probably that point up the top. I don't know if you remember that point up top, that feasible point, that extreme point up top. That's the one we're hitting now. Does that make sense? It's moved from this point to that point, if you recall. Okay. Let's go back to where it was. Let's go back to 8 and 5. Okay. And you might say, well, that was a lot of work, Dr. Miko, and you'd be right. If I have to do 5 or 6 of these for homework, which you do, how do I do that? Well, in my workbook, okay, this is my workbook, and I'm gonna rename this worksheet to, I don't know, this is Galaxy, right? Industry. And maybe even I'll make it a nice color. I'll do that one green. Now what's real nice is a lot of these work the same way. So I'm going to make a copy of that sheet. And I know some of you guys use Excel every day. A couple ways I can do that. I can right click on it and say move or copy, and then check create a copy and say where I want to move it to. I'm going to click OK. And you see now it has Galaxy Industry, the original, and Galaxy Industry 2. I'm just going to delete that because I'm going to show you another way to do it. The other way I can do that is if I hold down a control key and left click, you see it has that plus. See a little spreadsheet and a plus? You guys see that by my mouse? Can you see that? Yes, down the bottom. Well, it's saying, hey, you're just control key and click and left click. It's saying, hey, you just picked up a copy of this. Where do you want to drop it? I'm going to drop it right after. I'm just dropping it there. So it's a little easier, right? Control, and so now I have a copy of it. So this one I'm going to call, well, the next one we're going to do, which is this one. Okay, so what is it? Another computer manufacturer. So let's call this. Let's rename it to computer manufacturer. Okay, I'm going to make my tab color different. So let's take a look at this one, okay? And it says a computer company produces 2 types of computers. Each type of computer will require assembly time, inspection time, and storage space. The amount of each of these resources that can be devoted to the production of computers is listed. The manager wants to determine the quantity of each computer to produce to maximize the profit generated by sales. In order to develop a suitable model of the problem, the manager has met with design and manufacturing personnel. As a result of those meetings, the manager obtained the following information. We're making type 1 and type 2 here. We make $60 per profit for the type 1s, $50 profit for the type 2s. Assembly time is $4 hours for type 1, 10 for type 2. Inspection time is 2 and 1 respectively. Storage space is 3 cubic feet for each. And we have the following resources available: assembly time, inspection time, and storage space. So what's beautiful about this is I can change this. You know, I already have a model that works, right? So I'm going to change space rays to type 1. And let's change zappers to type 2. I'll redefault this to 1 and 1. But let's see, my profit coefficients, were 60 and 50 respectively. So let's change that 8 to 60 and that 5 to 50. Let's see what else we got going on. What are the things holding us back? Well, looks like time, right? We have assembly time, 4 and 10, and we have 100 hours. So let's call plastic assembly, and that's 4 and 10, and we have 100 hours. And everything is still right? So 10, 10, that's the profit I make, and that's the assembly time I use. Inspection time takes 2 and 1, and I have 22 hours. So I'll change this to inspection. I have 2 and 1, and I have 22 hours. I have storage space. Each takes 3 and 3 respectively, and I have 39 cubic feet. So I'm going to say space 3, 3, 39. Now I have an extra constraint down there, so I can do a couple things. I can clear it, which will leave it as like kind of a bad reference in my solver, or I could like obliterate it by deleting it. So if I right click on row 9 and click delete, hopefully that'll do what it needs to do. So it's gone. And my model is working the same way the other one worked, and it's a different deal. Let's go to solver, and this is nice because solver, hey, you're maximizing E4. Yep, we're still maximizing E4. C2 and D2, we're still changing those, yeah. And we're also E6 through E8 has to be less than or equal to G6 through G8. And that's exactly what we want. So we had a model that worked. We replicated that model, changed some values appropriately. We click solve. Solver finds a solution. And in this case, it said make 9 and 4. That gives you 740 bucks. Looks like I'm using all my inspection time and all my space. And I believe, yes, it is. That is the correct answer. So the other thing we could run into, okay? So what I'm trying to encourage you to do is, use a workbook and have all your, all your problems in one workbook, and you got one working, you copy it and modify it. So let's say this didn't happen, but let's say Dr. Miko decides to make a third type of computer, okay? What's nice about this is if I click on column D and do insert, okay, it'll insert it between type 1 and 2, and I want to insert it in the middle because what happens when I insert in the middle is look at all my sum products. What did they do? They expanded out appropriately. So now let's say this was a type 3 computer. I know they're not in order, but bear with me. And let's say, I don't know, let's just repopulate these as 1 and 1, and let's say this is, let's make it $80. Let's say it uses 7 hours, 1.5, and let's just go with 3. So because I insert it in the middle of those arranges or those arrays, everything got adjusted. Now I'm maximizing F4 instead of E4. My variable cells I'm changing are now C2 through E2, and F6 through F8 has to be less than or equal to H6 through H8. So because I smartly inserted in the right place, it adjusted all my formulas appropriately. Now I solve, now it says make 13 type 3s and the hell with 1s and 2s. Okay, so there's once you have something working, you don't have to reinvent the wheel every time is what I'm telling you. Does that make sense? There's always ways to do it. And even if I were trying to, I don't know, minimize something, I could still rip this off. Now, if I'm trying to minimize something, I really haven't showed you this yet, but if I'm trying to minimize a cell, I just change this option button from max to min, and it's the same kind of thing. So, it may seem difficult. You say, I'm not familiar with Excel, but like I said, we kind of do the same thing over and over again. Does that make sense? You guys understand what we're doing there? Okay, go ahead.
My computer's lagging, so I didn't even get from like some product on.
Okay.
And I'm not really good with Excel, so I'm kind of like,
okay.
Right now. So is there any way I can go over it? I can go over again. C2 plus D2 equals some product.
Okay, so
The formula. Yeah, I'm totally lost.
that's all right. Yeah, that's fine. What we can do is, what I try to do is we don't have like we only meet once a week, and so you guys come to campus maybe once a week. Some of you work on campus and here all the time, but what I try to do is like after class, like leave some time to like use as lab time or personal like office hours. So we can look at that then if that's all right.
All right. Yeah, that's fine.
Okay. So, any other questions? You guys have any other specific questions on this? Now, here's what we're going to focus on in the homework. So, well, now there's one other thing I want to cover before we are done. Okay, so I'm going to go to the end here. So the thing in the middle we're going to skip. Okay. So there's other things, we're going to cover the thing in the middle in chapter 2, which is sensitivity analysis next week. But there's other things that you can occur that you get weird kind of messages from Excel Solver, and I want to kind of explain what those are. Infeasibility occurs when a model has no feasible point. Okay, so if you design your constraints in such a way, you say it has to be less than or equal to these two constraints, and greater than or equal to this line, well, there's no points that simultaneously satisfy both of those regions. Unfortunately, Excel just says, hey, there's nothing possible here, right? If I would have said, for example, in the corn and barley, if I'd have said, I want to make sure that I make at least, 500 acres of barley, it would have told me infeasible because it says, you only have 80 acres, right? So it told me infeasible, no feasible solution found. So you might see that. That means it's overly constrained. Like the constraint's saying, this is impossible. There's no solution to this, okay? So you may see that. The other thing you could see is unboundedness. This is when there's too many solutions. If I say, hey, x1 has to be greater than or x2, and that's all I have in there, well, it's going to say create an infinite amount of space rays, infinite amount of zappers, you're going to make an infinite amount of money, but it gives you, that's not possible. It knows there's a problem. This is what we're saying, unbounded solution, like, hey, it goes on forever and ever. And what Excel does is it gives you this message, which is not an ugly message, but this means it's unbounded. It says the set cell values do not converge, meaning, it's not converging into a feasible region. It's going on forever and ever and ever, okay? So that's the second thing that you may encounter and may get frustrated with, but that's what it is. And we're going to talk more about this next week, but the third thing is you might find alternate optimal solutions. And what I mean by that is, if you think about it, I'm trying to draw, that's a pretty bad drawing of our feasible region, right? And my profit line maybe had this slope, and I'm pushing it out, and I said, hey, this is the last point it touches. It looks like that, right? Well, what happens if that profit line has the exact same slope as a constraint? Well, the last point it touches is not that one point, but it's all of those points. So not only is this an optimal solution, but so is this, 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 so is this. So Excel doesn't do a good job of saying, hey, you have multiple optimal solutions. Next week, we're going to learn to read the sensitivity report, and we'll determine, hey, this is a situation where we have multiple or alternate solutions. Not just one solution, but multiple solutions that give us the same optimal solution. Does that make sense? All right, so for homework for next week, what I would like you to do, and this is chapter 2, and this is all with Excel, okay? This is all with Excel. On pages 101 through 110 of your course text, please complete the following, okay? Number 2, part A only, just do part A, we'll do part B and C next week. Number 3, part A only. 7, 10, and 17. And in 17, it says month. That's a typo. It should say money. Okay, so if you see month in there, start with money. And 28. So do those with Excel Solver for next week. Next week, we're staying in chapter 2, and we're going to learn sensitivity analysis. So we're going to add on to this. Any questions on where we're at? And by the way, I think I told you guys I record every lecture. So last week, if you want to relive that, 8:23, you just click on that link, it goes to YouTube. You can hear me, you can watch me, you can relive what we did with Solver. So if you're struggling, so that might be a good thing to look at, to watch. And today I tried to capture everything on the document camera as well, so you have that. So I hope you have a good evening and a great week.
So homework all in Excel.
Yeah, do it all in Excel. Yeah.
I have a question to ask you. Is that copy book in the library? I ordered it, but it's not here yet.
What do you?
So to do homework, I ordered the book, it's just not here yet.
Oh, okay.
I didn't want to get too far behind doing the homework and
Yeah.
everything else. I didn't know if you had an extra copy book or if there was one in the library.
Yeah, I'll give you. I think I have one in my office, so I'll loan this one to you. Okay.
Oh, thank you very much.
Go ahead, you borrow that one. I think I have another one in my office. So that'll be easier next.
All right,
okay?
thanks a lot, I appreciate it. You gotta remember all my Excel.